Imagine looking up at the night sky and spotting a star that doesn't behave like any other. Its light flickers unpredictably, dimming in ways that defy explanation. What if I told you this isn't just a random cosmic quirk, but a potential clue to one of the greatest mysteries of the universe? Welcome to the strange and fascinating world of Dyson Sphere Candidates, megastructures so advanced they could only be the work of civilizations far beyond our imagination. In this video, we're diving into 25 specific space mysteries that challenge everything we think we know about the cosmos. From stars with bizarre light patterns to the tantalizing possibility of alien engineering, we'll explore the evidence, the theories, and the unanswered questions that keep scientists and dreamers alike staring at the stars. Stay with us, because by the end of this journey, you'll see the universe in a whole new light, and you might just find yourself wondering if we're truly alone. Let's begin. Now, let's take a closer look at the idea that started it all, the concept of Dyson spheres. Picture this: a civilization so advanced that it has outgrown the need for planets and instead builds a colossal structure around an entire star to capture its energy. This is the vision proposed by physicist Freeman Dyson in the 1960s. A Dyson sphere, in its simplest form, is a hypothetical megastructure designed to encase a star, allowing a civilization to harness nearly all of its energy output. Think of it as the ultimate power source, capable of sustaining a society far beyond our current technological capabilities. But why would a civilization need such a thing? As societies grow and their energy demands increase, they would eventually exhaust the resources of their home planet. A Dyson sphere offers a solution, a way to tap into the virtually limitless energy of a star. This concept isn't just about energy, though. It's also a key piece in the search for extraterrestrial intelligence, often referred to as SETI. If such megastructures exist, they would emit unique signatures like excess infrared radiation that we could potentially detect from Earth. In other words, finding a Dyson sphere could be our first real evidence of intelligent life beyond our solar system. Freeman Dyson's idea wasn't just a flight of fancy. It was grounded in the understanding of how civilizations might evolve. He suggested that as a society advances, its energy needs would grow exponentially, pushing it to find more efficient ways to harness power. A Dyson sphere represents the pinnacle of that evolution, a feat of engineering so grand that it challenges our imagination. And while we haven't found one yet, the search for these megastructures continues to inspire scientists and dreamers alike, offering a tantalizing glimpse into what might be possible in the far reaches of the universe. So, as we explore these space mysteries, keep in mind that the concept of Dyson spheres isn't just about energy. It's about the potential for civilizations to reach heights we can barely comprehend. And who knows, the next star we observe might just hold the key to unlocking one of the universe's greatest secrets. Now, let's turn our attention to the first star that sparked serious debate about the possibility of Dyson spheres, KIC 8,462,852, better known as Tabby star. Discovered by the Kepler Space Telescope, this star quickly became famous for its bizarre and unpredictable dimming patterns. Unlike most stars, which dim in regular, predictable ways due to orbiting planets, Tabby's star dims erratically, sometimes by as much as 22%. This unusual behavior has left scientists scratching their heads and sparked a flurry of theories, ranging from natural explanations to the tantalizing possibility of an artificial megastructure. One of the leading natural explanations involves dust. Some researchers suggest that the star might be surrounded by a massive cloud of dust or debris, perhaps from a collision between planets or the remnants of a disintegrating comet. This dust could block the star's light in irregular patterns, causing the strange dimming we observe. Another theory points to the star itself, proposing that its internal dynamics or magnetic activity might be responsible for the fluctuations. While these natural explanations are plausible, they don't fully account for the star's extreme and irregular dimming, leaving room for more speculative ideas. This is where the Dyson Sphere hypothesis comes into play. Some scientists have suggested that the dimming could be caused by a massive artificial structure, like a partial Dyson sphere or a swarm of energy collecting satellites orbiting the star. These structures, designed to capture the star's energy, could block its light in unpredictable ways, creating the unusual dimming patterns we see. While this idea is undeniably exciting, it's important to approach it with caution. Extraordinary claims require extraordinary evidence, and so far, no definitive proof of an artificial megastructure has been found. What makes Tabby's star so fascinating is that it challenges our understanding of both natural and artificial phenomena. It's a reminder that the universe is full of surprises, and sometimes the most intriguing mysteries lie in the details we can't yet explain. Whether the answer turns out to be dust, stellar activity, or something far more extraordinary, Tabby's star continues to captivate scientists and space enthusiasts alike, offering a glimpse into the complexities of the cosmos. And as we continue to study it, we might just uncover clues that bring us closer to answering one of humanity's oldest questions: are we alone in the universe? As we delve further into the enigma of Tabby's star, it's worth noting that the latest research continues to fuel both curiosity and debate. Recent studies have focused on refining our understanding of the star's dimming patterns, using advanced tools and techniques to gather more precise data. One of the most compelling findings is the discovery of long-term dimming trends, where the star's brightness has been observed to decrease gradually over years. This adds another layer of complexity to the mystery, as it suggests that whatever is causing the dimming isn't just a one-time event but an ongoing process. One of the leading explanations remains the presence of dust. Observations from the Hubble Space Telescope and other instruments have detected evidence of fine dust particles around the star, which could be responsible for the irregular dimming. This dust might originate from a massive asteroid belt, a disintegrating planet, or even a swarm of comets. While this theory is plausible, it still struggles to fully explain the star's extreme and erratic behavior. For instance, why would dust cause such dramatic and unpredictable dips in brightness? And why hasn't the dust dissipated over time, given the star's intense radiation? Another intriguing angle involves the star's own activity. Some researchers propose that Tabby's star might be undergoing unusual stellar processes, such as magnetic storms or internal instabilities, that could cause its light to fluctuate. However, this explanation also falls short of accounting for the star's most extreme dimming events, which seem too drastic to be caused by stellar activity alone. This leaves the door open for more speculative ideas, including the possibility of artificial structures. The Dyson Sphere hypothesis, while still speculative, remains a tantalizing explanation. If an advanced civilization were building a megastructure around Tabby's star, it could explain the irregular dimming patterns. Imagine a vast array of energy collecting satellites or panels orbiting the star, occasionally blocking its light as they move or adjust. While this idea captures the imagination, it's important to emphasize that no direct evidence of such a structure has been found. Scientists continue to approach this hypothesis with caution, prioritizing natural explanations while keeping an open mind to extraordinary possibilities. What keeps Tabby's star at the forefront of Dyson Sphere research is its uniqueness. No other star observed so far exhibits such extreme and irregular dimming, making it a prime candidate for further investigation. As new telescopes and technologies come online, such as the James Webb Space Telescope, we may finally gather the data needed to solve this cosmic puzzle. Whether the answer lies in natural phenomena or something more extraordinary, Tabby's star reminds us that the universe is full of mysteries waiting to be unraveled. And as we continue to explore, we inch closer to understanding not just this star, but the broader question of whether intelligent life exists beyond our planet. Now, let's turn our attention to another fascinating star that has captured the curiosity of astronomers, Epic 204,278,916. Unlike Tabby's star, which has become famous for its irregular dimming patterns, Epic 204,278,916 stands out for its extreme and erratic light fluctuations. This young star, located in the upper Scorpius star-forming region, has been observed to dim by as much as 65% of its brightness in just a single day. Such dramatic changes are not only rare but also raise intriguing questions about what could be causing them. One of the key differences between Epic 204,278,916 and Tabby's star lies in their ages and environments. Epic 204,278,916 is a young star, estimated to be only around 11 million years old, surrounded by a protoplanetary disk, a swirling cloud of gas and dust from which planets might form. This disk could play a significant role in the star's erratic behavior. Some scientists suggest that the dimming might be caused by clumps of material within the disk passing in front of the star, temporarily blocking its light. Alternatively, the star's own magnetic activity, which is often more intense in young stars, could be contributing to these sudden drops in brightness. However, the sheer scale of the dimming events observed around Epic 204,278,916 makes it a compelling candidate for further investigation. While natural explanations like dust or stellar activity are plausible, the extreme nature of the fluctuations has led some to wonder if something more extraordinary could be at play. Could these light dips be evidence of a massive artificial structure, like a Dyson sphere under construction? The idea is speculative, but it's not entirely out of the question. If an advanced civilization were building a megastructure around this young star, it might explain the irregular and dramatic changes in brightness. What makes Epic 204,278,916 particularly interesting is how its behavior contrasts with Tabby's star. While Tabby's star exhibits long-term dimming trends alongside its irregular dips, Epic 204,278,916 fluctuations are far more sudden and extreme. This difference suggests that the mechanisms behind their dimming might not be the same, adding another layer of complexity to the search for Dyson Sphere Candidates. It also highlights the diversity of cosmic phenomena that scientists must consider when exploring the possibility of extraterrestrial megastructures. As with Tabby's star, the search for answers continues. Future observations, particularly with next-generation telescopes, could shed more light on the true nature of Epic 204,278,916 erratic behavior. Whether the explanation lies in natural processes or something more extraordinary, this star serves as a reminder of how much we still have to learn about the universe. And as we uncover more about these mysterious objects, we move closer to answering one of humanity's most profound questions: are we alone in the cosmos? Now, let's take a closer look at the natural explanations behind Epic 204,278,916 puzzling behavior. While the idea of a Dyson sphere is undeniably captivating, scientists have proposed several more grounded theories to account for the star's dramatic dimming. One leading hypothesis points to the presence of planetary debris or clumps of material within its protoplanetary disk. As this young star continues to evolve, large chunks of dust and gas could occasionally pass in front of it, blocking its light and causing those sudden, extreme drops in brightness. This explanation aligns with what we know about young stars, as they often have chaotic environments filled with swirling debris. Another possibility lies in the star's own magnetic activity. Young stars like Epoch 204,278,916 are known to have strong magnetic fields, which can lead to intense stellar flares and other forms of magnetic turbulence. These events could cause temporary but significant changes in the star's brightness, creating the erratic patterns we observe. While this might sound less exciting than the idea of an alien megastructure, it's a reminder of how dynamic and unpredictable young stars can be. What makes Epoch 204,278,916 so intriguing, however, is the sheer scale of its dimming events. Even with these natural explanations, the star's behavior pushes the boundaries of what we typically see in similar systems. For instance, while other young stars with protoplanetary disks do exhibit some variability, none have shown fluctuations as extreme as Epoch 204,278,916. This discrepancy keeps scientists on their toes, prompting them to consider whether there's something unique about this star or if we're missing a piece of the puzzle. The ongoing fascination with Epoch 204,278,916 also stems from its potential to teach us more about the early stages of star and planet formation. By studying its erratic behavior, astronomers can gain insights into how planetary systems evolve and what kinds of processes might be at play during their infancy. This star serves as a natural laboratory, offering a rare glimpse into the chaotic environments where planets are born. Yet, despite the compelling natural explanations, the possibility of something more extraordinary, like a Dyson sphere, lingers in the background. The extreme nature of the dimming events keeps the door open for speculation, ensuring that Epoch 204,278,916 remains a star worth watching. As we continue to observe and analyze this enigmatic object, we're reminded that the universe is full of surprises, and sometimes the most ordinary explanations can lead to extraordinary discoveries. Shifting our gaze to another intriguing star, we now turn to Tycho 6111-1162-1, a celestial object that has captured the attention of astronomers for its unusual light patterns. Unlike the erratic dimming of Epoch 204,278,916 or the mysterious fluctuations of Tabby's star, Tycho 6111-1162-1 presents a light curve that is both puzzling and distinct. Its brightness dips in a way that doesn't neatly align with typical stellar behavior, sparking curiosity about what might be causing these anomalies. One of the standout features of Tycho 6111-1162-1 is the irregularity of its dimming events. While many stars experience predictable changes in brightness due to factors like rotation or orbiting planets, this star's light curve shows dips that are inconsistent in both timing and depth. These irregularities have led some researchers to consider the possibility of an artificial megastructure, such as a Dyson sphere, as a potential explanation. The idea is that a massive structure orbiting the star could intermittently block its light, creating the unusual patterns we observe. However, Tycho 6111-1162-1 also presents challenges that make it a complex candidate to study. For one, it's located at a significant distance from Earth, which limits the amount of detailed data we can gather. Additionally, its light curve doesn't perfectly match the expected signatures of a Dyson sphere, leaving room for alternative explanations. Some scientists suggest that the star's behavior could be caused by natural phenomena, such as a swarm of comets or a dense ring of debris passing in front of it. Yet, the sheer unpredictability of its dimming keeps the door open for more extraordinary possibilities. What makes Tycho 6111-1162-1 particularly fascinating is its potential to challenge our understanding of stellar behavior. If its light curve is indeed the result of a Dyson sphere or another megastructure, it would represent a groundbreaking discovery offering evidence of advanced extraterrestrial engineering. On the other hand, if natural causes are at play, studying this star could reveal new insights into the diverse ways stars and their surrounding environments can evolve. As we continue to monitor TYC 6111-1162-1, it serves as a reminder of how much we still have to learn about the cosmos, whether its mysteries are explained by natural processes or something more extraordinary. This star remains a compelling piece of the puzzle in our search for Dyson Sphere Candidates. And as we move forward, each observation brings us one step closer to unraveling the secrets of this enigmatic object. Now, let's take a closer look at the hurdles scientists face when studying TYC 6111-1162-1. One of the biggest challenges is its sheer distance from Earth. Located thousands of light-years away, this star is far beyond the reach of our most advanced telescopes for detailed observation. While we can detect its light and analyze its patterns, the data we receive is limited, making it difficult to draw definitive conclusions about what's happening around it. Adding to the complexity is the fact that current technology has its limits. Even with powerful instruments like the Kepler Space Telescope, which first flagged TYC 6111-1162-1 as an object of interest, we're still working with incomplete information. The light curves we observe are like pieces of a puzzle, but without more precise measurements, it's hard to determine whether the dimming is caused by natural phenomena or something more extraordinary like a Dyson sphere. For instance, if the star is surrounded by a dense cloud of dust or debris, it could mimic the light-blocking effects of an artificial structure, making it tricky to distinguish between the two. Another issue is the irregularity of the star's dimming events. Unlike predictable patterns caused by orbiting planets or stellar activity, TYC 6111-1162-1 light dips are sporadic and inconsistent. This unpredictability makes it harder to model and test potential explanations. Scientists have to consider a wide range of possibilities, from swarms of comets to massive rings of debris, each requiring different methods of analysis. And while these natural explanations are plausible, they don't fully account for the star's unique behavior, leaving room for more speculative theories. Despite these challenges, studying TYC 6111-1162-1 is far from a lost cause. In fact, it's precisely these mysteries that make it such a valuable target for research. Every observation, even with the limitations of current technology, brings us closer to understanding what's really going on. Future advancements in telescope capabilities, such as the James Webb Space Telescope, could provide the sharper, more detailed data needed to crack the case. Until then, TYC 6111-1162-1 remains a tantalizing enigma, pushing the boundaries of our knowledge and keeping the search for Dyson Sphere Candidates alive. As we continue to explore this star, it's a reminder of how much we still have to learn about the universe. Whether its secrets lie in natural phenomena or something beyond our current understanding, TYC 6111-1162-1 challenges us to think bigger and dig deeper. And in doing so, it keeps the flame of curiosity burning bright, driving us to uncover the truth behind one of space's most intriguing mysteries. Now, shifting our focus to a crucial piece of the puzzle, let's explore how infrared signatures play a vital role in the search for Dyson spheres. When we think about these megastructures, one of the most telling clues lies in the heat they would emit. If an advanced civilization were to build a Dyson sphere around a star to harness its energy, the structure would inevitably absorb and re-radiate some of that energy as heat. This excess heat would show up as infrared emissions, making it a key indicator for scientists searching for these cosmic constructs. Infrared light, which is invisible to the human eye, is essentially the thermal radiation given off by objects as they release heat. In the case of a Dyson sphere, the energy collected from the star will be converted into usable power, but some of it would escape as waste heat. This heat would radiate outward, creating a distinct infrared signature that telescopes can detect. Unlike visible light, which can be blocked or obscured, infrared emissions are harder to hide, making them a reliable marker for potential Dyson Sphere candidates. To identify these signatures, scientists rely on specialized instruments designed to detect infrared light. One of the most notable tools in this effort is the Wide Field Infrared Survey Explorer, or WISE, a space telescope launched by NASA. WISE has scanned the skies, cataloging millions of objects and searching for unusual infrared patterns that could point to the presence of a Dyson sphere. By analyzing the data, researchers can pinpoint stars that emit more infrared radiation than expected, flagging them as potential candidates for further study. However, it's not as simple as just looking for excess heat. Natural phenomena like dust clouds or young stars surrounded by debris can also produce significant infrared emissions. This means scientists have to carefully rule out these possibilities before concluding that a star's infrared signature might be linked to an artificial megastructure. It's a meticulous process requiring a combination of data analysis, modeling, and cross-referencing with other observations. Despite these challenges, the search for infrared signatures remains one of the most promising methods in the hunt for Dyson spheres. It's a fascinating example of how we can use the laws of physics to guide our search for extraterrestrial intelligence. By focusing on the heat these structures would inevitably produce, we're not just looking for evidence of advanced civilizations, we're also pushing the boundaries of our understanding of the universe. And as technology continues to advance, the possibility of detecting these elusive signatures grows ever closer, bringing us one step nearer to answering the age-old question, are we alone? Now, let's take a closer look at how scientists actually go about detecting these infrared signatures in space. The process is far from simple, and it relies on some of the most advanced technology we have at our disposal. One of the standout tools in this effort is the Wide Field Infrared Survey Explorer, or WISE, a space telescope launched by NASA in 2009. WISE was designed to map the entire sky in infrared light, capturing the faint heat signatures of countless celestial objects. Over its mission, it has provided an invaluable treasure trove of data, helping researchers identify stars with unusual infrared emissions that could hint at the presence of a Dyson sphere. But WISE isn't the only instrument in the game. Other observatories like the Spitzer Space Telescope and the James Webb Space Telescope have also played crucial roles in this search. These telescopes are equipped with highly sensitive infrared detectors, allowing them to pick up even the faintest traces of heat. By comparing the infrared data from these telescopes with observations in other wavelengths, scientists can build a more complete picture of what's happening around a star. For example, if a star shows an excess of infrared light but no corresponding increase in visible light, it could be a sign that something unusual, like a Dyson sphere, is blocking or re-radiating that energy. The process of analyzing this data is incredibly detailed. Scientists use sophisticated algorithms to sift through the vast amounts of information collected by these telescopes, looking for patterns that stand out. They also create models to simulate what a Dyson sphere's infrared signature might look like, comparing these predictions to the actual data. This helps them distinguish between natural phenomena like dust clouds or young stars and potential artificial structures. It's a bit like solving a cosmic puzzle where every piece of data brings us closer to understanding what's really out there. Of course, the search isn't without its challenges. Infrared observations can be affected by interference from Earth's atmosphere, which is why space-based telescopes like WISE are so important. Even then, the data can be noisy, and interpreting it requires a great deal of expertise. But despite these hurdles, the progress made so far is remarkable. Each new observation adds to our growing understanding of the universe and brings us one step closer to answering the question of whether we're truly alone. As we continue to refine our methods and develop even more advanced tools, the search for Dyson spheres through infrared observations remains one of the most exciting frontiers in astronomy. It's a testament to human ingenuity and our relentless curiosity about the cosmos. And who knows, the next breakthrough could be just around the corner, waiting to reveal the secrets of an advanced civilization far beyond our own. Now, shifting our gaze to one of the most profound questions in astronomy, let's explore how the search for Dyson spheres ties into the Fermi paradox. Named after physicist Enrico Fermi, this paradox asks a simple yet haunting question. If the universe is so vast and filled with countless stars and planets, why haven't we found any evidence of advanced civilizations? The sheer scale of the cosmos suggests that intelligent life should be abundant, yet our searches have come up empty. This contradiction lies at the heart of the Fermi paradox, and Dyson spheres play a fascinating role in this mystery. The idea of Dyson spheres offers a potential answer, or at least a clue. If advanced civilizations exist, they might harness the energy of their stars using megastructures like Dyson spheres. These structures would leave detectable signatures, such as unusual infrared emissions, which we've been searching for. But here's the twist: despite decades of looking, we haven't found definitive proof of such structures. This absence raises even more questions. Are we looking in the wrong places? Are our methods not advanced enough? Or could it be that advanced civilizations are so rare or so different from us that they remain hidden? One possibility is that civilizations capable of building Dyson spheres might not last long enough for us to detect them. They could self-destruct through war, environmental collapse, or other catastrophes before they reach the technological level required to construct such megastructures. Alternatively, they might evolve beyond the need for Dyson spheres, developing energy sources or technologies we can't even imagine. This line of thinking suggests that the absence of evidence might not be evidence of absence, but rather a reflection of our limited understanding. Another angle to consider is the timescale of the universe. Stars and galaxies have existed for billions of years, but intelligent life might be a fleeting phenomenon. Civilizations could rise and fall in the blink of an eye on a cosmic scale, making it unlikely for two advanced societies to exist simultaneously. This idea, known as the Great Filter, suggests that there might be a critical barrier, either behind us or ahead of us, that prevents civilizations from reaching the stars. If the filter lies ahead, it could mean that our own future is uncertain. The search for Dyson spheres, then, isn't just about finding alien megastructures. It's about grappling with the deeper implications of the Fermi paradox and what it means for humanity's place in the universe. Every observation, every piece of data, brings us closer to understanding whether we're alone, or whether the silence of the cosmos is hiding something extraordinary. As we continue to explore, we're not just searching for answers about other civilizations, we're also uncovering clues about our own destiny, and that makes this one of the most compelling mysteries in all of science. Now, let's take a step into the realm of cosmic classification with the Kardashev scale. Proposed by Soviet astronomer Nikolai Kardashev in the 1960s, this scale offers a fascinating way to measure the technological advancement of civilizations based on their energy consumption. It's a framework that helps us imagine what truly advanced societies might look like, and where humanity stands in the grand scheme of things. The Kardashev scale divides civilizations into three main types. A Type 1 civilization, also known as a planetary civilization, has mastered the ability to harness all the energy available on its home planet. Think of controlling weather, tapping into geothermal energy, or even harnessing the power of earthquakes. Humanity, for context, is still working toward this level, as we currently rely on only a fraction of Earth's energy potential. Moving up the scale, a Type 2 civilization or stellar civilization has achieved the ability to harness the total energy output of its star. This is where Dyson Spheres come into play. A Type 2 civilization would likely construct megastructures like Dyson Spheres to capture and utilize the immense energy radiating from their star. These structures would allow them to power advanced technologies, interstellar travel, and perhaps even reshape their solar system to suit their needs. The idea of a Dyson Sphere isn't just science fiction, it's a logical step for a civilization that has outgrown the energy limits of its planet. At the top of the scale is a Type 3 civilization, or galactic civilization, capable of harnessing the energy of an entire galaxy. Such a society would have technologies far beyond our current understanding, possibly manipulating black holes, traveling between stars, or even creating new galaxies. While this level of advancement remains purely theoretical, it sparks the imagination and raises questions about the ultimate potential of intelligent life. So, where does this leave us in the search for Dyson Spheres? If we were to detect a Dyson Sphere, it would likely be the work of a Type 2 civilization. Such a discovery wouldn't just confirm the existence of advanced extraterrestrial life, it would also provide a glimpse into humanity's potential future. Could we one day build our own Dyson Sphere? The answer lies in our ability to innovate, collaborate, and overcome the challenges that come with harnessing such vast amounts of energy. The Kardashev scale reminds us that the universe is full of possibilities, and the search for Dyson Spheres is more than just a hunt for alien megastructures. It's a journey to understand the limits of technology, the potential of civilizations, and our own place in the cosmos. As we continue to explore, we're not just looking for answers about others, we're also uncovering what it means to be a civilization on the rise. And that's a story worth telling. Now, let's shift our focus to one of the most intriguing debates in the search for Dyson Spheres, the question of natural versus artificial explanations. When we observe unusual phenomena in space, like the strange dimming patterns of stars such as KIC 8462852 or EPIC 204278916, scientists are faced with a critical challenge. Are these anomalies the result of natural cosmic processes, or could they be evidence of advanced alien technology? This debate lies at the heart of the search for Dyson Spheres, and it's a reminder of the importance of scientific skepticism. On one side of the debate, natural explanations often provide the most straightforward answers. For example, the irregular dimming of stars could be caused by massive clouds of dust or debris orbiting the star. These clouds might be remnants of planetary collisions, cometary swarms, or even the remnants of a protoplanetary disk. Such phenomena are well documented in astronomy, and they don't require the existence of extraterrestrial intelligence to explain. In fact, many of the early theories about Tabby's star focused on natural causes, such as a swarm of comets or a circumstellar disk, before more exotic explanations were considered. On the other hand, the possibility of artificial explanations like the construction of a Dyson Sphere captures the imagination and pushes the boundaries of what we think is possible. If an advanced civilization were to build a megastructure around a star, it would likely cause irregular dimming as the structure blocks starlight. The idea is tantalizing, but it's also a hypothesis that requires extraordinary evidence. Scientists must carefully weigh the likelihood of natural causes against the more speculative idea of alien megastructures. This is where skepticism plays a crucial role. While it's exciting to imagine the discovery of a Dyson Sphere, researchers must rule out all possible natural explanations before concluding that something artificial is at work. This balance between curiosity and caution is what drives the scientific process. It's easy to get caught up in the excitement of potentially discovering alien technology, but science demands rigor and evidence. Every unusual observation must be scrutinized, tested, and retested. This approach ensures that our conclusions are based on solid data, not just wishful thinking. It's a reminder that the search for Dyson spheres isn't just about finding answers, it's about asking the right questions and being willing to accept that the truth might be more mundane than we hope. At the same time, the debate between natural and artificial explanations highlights the beauty of scientific exploration. It's a process that encourages us to think creatively while staying grounded in evidence. Whether the dimming of a star is caused by dust clouds or a Dyson sphere, each discovery brings us closer to understanding the universe and our place within it. And as we continue to explore, we're reminded that the search for knowledge is as much about the journey as it is about the destination. So, as we move forward, let's keep our minds open, our questions sharp, and our skepticism intact, because the truth is out there waiting to be uncovered. Now, let's turn our attention to an often overlooked but incredibly important aspect of the search for Dyson spheres, the role of citizen science. While professional astronomers and researchers play a central role in uncovering the mysteries of the cosmos, they're not alone in this quest. Ordinary people, armed with curiosity and a passion for discovery, have made significant contributions to the field through projects like Planet Hunters. These initiatives allow anyone with an internet connection to sift through vast amounts of astronomical data, searching for patterns that might indicate the presence of Dyson spheres or other cosmic anomalies. Citizen science projects like Planet Hunters rely on the collective power of thousands of volunteers to analyze data from telescopes such as Kepler and TESS. These telescopes capture light from distant stars, recording subtle changes in brightness that could signal anything from orbiting planets to potential megastructures. The sheer volume of data generated by these missions is staggering, far more than professional scientists can process on their own. That's where citizen scientists come in. By combing through this data, they help identify unusual patterns that might otherwise go unnoticed, bringing potential Dyson Sphere candidates to the attention of researchers. One of the most remarkable aspects of citizen science is its ability to democratize space exploration. It's not just about the discoveries themselves, it's about giving people from all walks of life the opportunity to contribute to something bigger than themselves. Whether it's a teacher in a small town, a student halfway across the world, or a retiree with a love for astronomy, anyone can participate. This collaborative approach not only accelerates the pace of discovery, but also fosters a sense of shared purpose and excitement about the mysteries of the universe. The impact of citizen science on the search for Dyson spheres has been profound. For example, some of the most intriguing candidates, like KIC 8462852, were first flagged by volunteers on platforms like Planet Hunters. These discoveries often spark further investigation by professional astronomers, leading to new insights and, in some cases, groundbreaking research. Citizen scientists have proven time and again that they're capable of spotting patterns and anomalies that even sophisticated algorithms might miss, highlighting the irreplaceable value of human intuition and curiosity. But the contributions of citizen scientists go beyond just identifying potential candidates. They also play a crucial role in refining our understanding of these phenomena. By participating in discussions, sharing observations, and collaborating with researchers, they help build a more comprehensive picture of what's happening in the cosmos. This partnership between professionals and amateurs is a testament to the power of collective effort, showing that the search for knowledge is a shared endeavor. As we look to the future, the role of citizen science in the search for Dyson spheres is only set to grow. With new telescopes and missions on the horizon, the amount of data available for analysis will continue to expand. Projects like Planet Hunters will need even more volunteers to help sift through this information, opening up new opportunities for discovery. And as technology advances, the tools available to citizen scientists will become even more powerful, enabling them to make even greater contributions to our understanding of the universe. So, the next time you gaze up at the stars, remember that you don't need a PhD or access to a high-powered telescope to be part of the search for cosmic mysteries. Thanks to citizen science, the universe is within reach for anyone with a curious mind and a willingness to explore. And who knows, the next big discovery, perhaps even the first confirmed Dyson Sphere, might just come from someone like you. As we continue our journey through the mysteries of Dyson Spheres, let's shift our gaze to the horizon of discovery. The future of searching for these cosmic megastructures is brighter than ever, thanks to groundbreaking technologies and missions poised to revolutionize our understanding of the universe. At the forefront of this new era is the James Webb Space Telescope, a marvel of modern science that promises to push the boundaries of what we can observe and comprehend. The James Webb Space Telescope, often referred to as Webb, is designed to peer deeper into space than any telescope before it. With its advanced infrared capabilities, Webb can detect the faint heat signatures that might be emitted by a Dyson sphere, even from vast distances. Unlike previous telescopes, Webb's sensitivity allows it to observe stars and their surroundings with unprecedented clarity, making it an invaluable tool in the search for these elusive structures. By analyzing the light from distant stars, Webb could uncover subtle anomalies that hint at the presence of megastructures, bringing us closer to answering one of the most profound questions in science: are we alone in the universe? But Webb is just the beginning. Upcoming missions like the Nancy Grace Roman Space Telescope, set to launch in the coming years, will further enhance our ability to scan the cosmos. Equipped with a wide-field instrument, the Roman telescope will survey large swaths of the sky, identifying potential Dyson Sphere candidates by detecting unusual patterns in starlight. Its ability to observe vast regions of space quickly and efficiently makes it a powerful ally in the search for extraterrestrial intelligence. On the ground, next-generation observatories like the extremely large telescope in Chile are also set to play a pivotal role. With its massive mirror, this telescope will capture incredibly detailed images of distant stars, allowing scientists to study their light in ways never before possible. By combining data from space-based and ground-based telescopes, researchers can cross-verify findings, reducing the chances of false positives and increasing the likelihood of making a genuine discovery. Advancements in data analysis are equally exciting. Artificial intelligence and machine learning algorithms are being developed to sift through the enormous amounts of data generated by these telescopes. These tools can identify patterns and anomalies far more efficiently than traditional methods, helping researchers focus their efforts on the most promising candidates. As these technologies continue to evolve, they will become even more integral to the search for Dyson spheres, enabling us to process and interpret data at an unprecedented scale. The future of Dyson sphere searches isn't just about technology, it's also about collaboration. International partnerships and interdisciplinary efforts are bringing together astronomers, physicists, engineers, and even citizen scientists to tackle this monumental challenge. By pooling resources and expertise, the global scientific community is creating a unified front in the quest to uncover the secrets of the cosmos. As we look ahead, the possibilities are as vast as the universe itself. Each new mission, each technological breakthrough, brings us one step closer to unraveling the mystery of Dyson spheres. Whether we find them or not, the journey itself is a testament to humanity's unyielding curiosity and determination to explore the unknown. And with every discovery, we inch closer to understanding our place in the grand tapestry of the cosmos. Now, let's turn our attention to a question that goes beyond science and technology. What happens if we actually find a Dyson sphere? The discovery of such a megastructure wouldn't just be a scientific breakthrough. It would raise profound ethical questions about how humanity should respond. Imagine the moment we confirm the existence of an advanced extraterrestrial civilization. What responsibilities would we have, and what risks might come with reaching out to them? One of the first ethical dilemmas would be deciding whether to make contact at all. On one hand, the opportunity to communicate with a civilization capable of building a Dyson sphere could unlock unimaginable knowledge and advancements for humanity. Sharing ideas, technology, and even cultural perspectives could propel us forward in ways we can't yet comprehend. But on the other hand, there's the risk of unintended consequences. What if their intentions aren't peaceful? What if our attempts to communicate inadvertently expose humanity to danger? These are questions that scientists, philosophers, and policymakers would need to grapple with. Another layer of complexity lies in the potential power imbalance. A civilization advanced enough to construct a Dyson sphere would likely be far more technologically sophisticated than we are. This raises concerns about exploitation or domination. Would we be seen as equals, or would we risk becoming subordinate to a more powerful species? History has shown us how encounters between advanced and less advanced civilizations on Earth have often led to conflict or exploitation. Could we avoid repeating those mistakes on a cosmic scale? There's also the question of who gets to speak for humanity. If we were to send a message or attempt contact, who would decide what to say? Would it be a collaborative effort involving nations, scientists, and ethicists, or would a single entity take the lead? The stakes are incredibly high, and the decisions made could shape the future of our species. Beyond the immediate concerns, there's the broader philosophical issue of how such a discovery would change our understanding of ourselves. Finding evidence of a Dyson sphere would confirm that we're not alone in the universe, fundamentally altering our perspective on life, intelligence, and our place in the cosmos. It could inspire unity and cooperation among humanity, or it could spark fear and division. How we handle this revelation would say as much about us as it does about the civilization we've discovered. As we ponder these ethical questions, it's clear that the search for Dyson spheres isn't just about science. It's about preparing for a future that could challenge our values, our priorities, and our very identity as a species. The journey to uncover these cosmic mysteries is as much about understanding ourselves as it is about understanding the universe. And as we move forward, we must do so with both curiosity and caution, ensuring that our actions reflect the best of what humanity has to offer. Now, shifting our gaze from the ethical implications, let's explore how Dyson spheres have captured the imagination of storytellers and creators, leaving a lasting mark on science fiction and popular culture. These megastructures, with their awe-inspiring scale and futuristic allure, have become a staple in narratives that push the boundaries of human imagination. From the pages of novels to the silver screen, Dyson spheres have served as both a symbol of technological ambition and a canvas for exploring profound questions about humanity's future. One of the earliest and most iconic appearances of a Dyson sphere in science fiction was in Larry Niven's 1970 novel Ringworld. While not a perfect sphere, Niven's megastructure captured the essence of the concept, inspiring countless writers to explore similar ideas. The sheer scale of these constructs, capable of harnessing the energy of an entire star, has made them a powerful metaphor for humanity's potential to transcend its limits. They represent not just technological achievement, but also the audacity to dream big. In film and television, Dyson spheres have often been portrayed as mysterious, almost mythical constructs. A standout example is the 1990 Star Trek, The Next Generation episode Relics, where the crew of the Enterprise discovers a massive Dyson sphere hidden in deep space. The episode not only showcased the visual grandeur of such a structure, but also sparked conversations about the engineering marvels and existential questions they embody. What would it mean to encounter such a creation? What kind of civilization could build it? These questions resonate deeply with audiences, blending science with wonder. Beyond their role in storytelling, Dyson spheres have also influenced how we think about space exploration and our place in the universe. They've become a shorthand for advanced civilizations, often appearing in discussions about the Fermi paradox and the search for extraterrestrial intelligence. By imagining civilizations capable of building such megastructures, science fiction encourages us to think beyond our current technological limitations and consider what might be possible in the distant future. The cultural impact of Dyson spheres extends even further, shaping public interest in space and inspiring real-world scientific inquiry. Concepts like these remind us that the line between science fiction and science fact is often blurrier than we think. After all, the idea of a Dyson sphere began as a thought experiment by physicist Freeman Dyson, and today it's a serious topic of discussion among astronomers and engineers. This interplay between fiction and reality keeps the public engaged, fueling curiosity and driving support for space exploration. As we reflect on the cultural legacy of Dyson spheres, it's clear that they've done more than just entertain. They've expanded our collective imagination. They challenge us to envision a future where humanity might one day build such wonders, while also reminding us of the mysteries that still lie beyond our reach. And as we continue to explore the cosmos, both in fiction and in reality, these megastructures will remain a powerful symbol of what it means to dream among the stars. Now, let's turn our attention to the staggering economics and engineering challenges behind building a Dyson sphere. Even for an advanced civilization, the sheer scale of such a project is almost beyond comprehension. To begin with, the materials required would be astronomical, literally. A Dyson sphere would need to encase an entire star, meaning the amount of raw material required would dwarf anything humanity has ever attempted to gather or construct. For perspective, if we were to build a Dyson sphere around our own sun, we'd need to dismantle entire planets, moons, and asteroids just to gather enough matter. Mercury, for example, might be a prime candidate for harvesting due to its proximity to the Sun, but even that would only provide a fraction of the necessary resources. Beyond the materials, the energy required to assemble such a structure is another monumental hurdle. Constructing a Dyson sphere would demand an energy output far beyond what any civilization currently possesses. Even if we could harness the energy of multiple stars, the logistics of coordinating such a project across vast distances of space would be mind-boggling. The construction process itself would likely take centuries, if not millennia, requiring a level of coordination and technological precision that we can barely imagine. Then there's the engineering itself. A Dyson sphere isn't just a giant shell around a star. It's a delicate balance of forces. The structure would need to withstand the gravitational pull of the star, the radiation it emits, and the potential for collisions with space debris. Maintaining stability over such a vast area would require materials and technologies that don't yet exist, possibly even new forms of matter or energy manipulation. And let's not forget the need for self-repairing systems, as any damage to the sphere could have catastrophic consequences. But perhaps the most intriguing challenge is the economic one. How would a civilization fund such a project? Even if we assume a post-scarcity society where resources are abundant, the allocation of time, labor, and intellectual capital would still be immense. The societal commitment required to undertake a Dyson sphere project would need to be unparalleled, with generations dedicating themselves to a vision that might not come to fruition for thousands of years. It's a testament to the audacity of such an idea, a project that transcends not just technology, but the very concept of time and human ambition. Despite these challenges, the idea of a Dyson sphere continues to captivate us because it represents the ultimate expression of a civilization's potential. It's a reminder that the boundaries of what we can achieve are limited only by our imagination and our willingness to push beyond them. And while the economics and engineering of building such a structure may seem insurmountable today, they also inspire us to dream of a future where such feats might one day be possible. While the Dyson Sphere remains one of the most iconic megastructures in theoretical science, it's far from the only idea that captures the imagination of futurists and scientists alike. Shifting our focus, let's explore some alternative megastructures that push the boundaries of what we think is possible. One such concept is the Dyson swarm, a variation on the classic Dyson sphere. Instead of a single, solid shell encircling a star, a Dyson swarm consists of countless individual satellites or habitats orbiting the star in a coordinated pattern. These smaller units could collect solar energy independently, offering a more flexible and potentially achievable design. Unlike a Dyson sphere, which requires an unimaginable amount of material and engineering precision, a Dyson swarm could be built incrementally, making it a more practical option for a civilization in the early stages of megastructure construction. Another fascinating idea is the Matryoshka brain, a structure designed not for energy collection but for computation. Imagine a series of nested shells surrounding a star, each one capturing and utilizing the star's energy to power an unfathomably powerful supercomputer. The innermost shell would absorb the star's raw energy, while the outer layers would radiate waste heat, creating a self-sustaining computational system. A Matryoshka brain could theoretically simulate entire universes or host the consciousness of an entire civilization, offering a glimpse into a future where intelligence and technology merge on a cosmic scale. Comparing these megastructures to a Dyson sphere reveals both their similarities and their unique challenges. While a Dyson sphere focuses on energy harvesting, a Dyson swarm emphasizes modularity and scalability, and a Matryoshka brain shifts the goal to computational power. Each structure reflects a different vision of what an advanced civilization might prioritize: energy, flexibility, or intelligence. Yet all of them share the same underlying ambition: to harness the power of stars and transcend the limits of planetary existence. These alternative megastructures also highlight the diversity of thought in theoretical science. They remind us that the future of technology isn't confined to a single path, but is instead a vast landscape of possibilities, each with its own set of challenges and rewards. Whether it's the elegance of a Dyson swarm or the computational might of a Matryoshka brain, these ideas inspire us to think beyond the stars and imagine what humanity, or any civilization, might one day achieve. Now, let's take a step back and revisit one of the most famous tools in the search for extraterrestrial intelligence, the Drake equation. Proposed by astronomer Frank Drake in the 1960s, this equation attempts to estimate the number of active, communicative civilizations in our galaxy. It considers factors like the rate of star formation, the fraction of stars with planets, and the likelihood of life developing on those planets. While the Drake equation doesn't provide a definitive answer, it offers a framework for thinking about the possibilities of intelligent life beyond Earth. So, where do Dyson spheres fit into this equation? If we were to discover a Dyson sphere or any similar megastructure, it would dramatically alter our understanding of the equation's variables. For instance, it would suggest that advanced civilizations not only exist, but have reached a level of technological sophistication capable of harnessing the energy of an entire star. This discovery would shift our perspective on the likelihood of intelligent life surviving long enough to develop such technologies, a key factor in the Drake equation. Moreover, finding a Dyson sphere would imply that civilizations can overcome the challenges of resource depletion, environmental collapse, and self-destruction issues that often dominate discussions about the longevity of intelligent life. It would also raise questions about the frequency of such civilizations in the universe. Are Dyson spheres rare, or are they a common milestone for advanced species? The answer could reshape our estimates of how many civilizations might be out there, waiting to be discovered, but the implications go even deeper. If Dyson spheres are indeed a sign of highly advanced civilizations, their discovery could help us refine the Drake equation by providing real-world data to replace some of its speculative variables. Instead of guessing how many civilizations might exist, we could begin to draw conclusions based on observable evidence. This would not only validate the equation as a tool, but also bring us closer to answering one of humanity's oldest questions: are we alone in the universe? As we continue to explore the cosmos, the search for Dyson spheres and other megastructures remains a thrilling avenue for discovery. Each candidate we investigate brings us one step closer to understanding the true scope of intelligent life in the universe. And while the Drake equation may not yet have all the answers, the potential discovery of a Dyson sphere could be the key to unlocking its mysteries. Now, shifting our focus to the cutting-edge tools reshaping the search for Dyson spheres, let's explore the role of artificial intelligence in this cosmic detective work. With the sheer volume of data collected by telescopes and space observatories, analyzing every piece of information manually is simply impossible. This is where artificial intelligence steps in, offering a powerful solution to sift through the noise and uncover potential candidates. Artificial intelligence, particularly machine learning algorithms, has become indispensable in modern astronomy. These systems are trained to recognize patterns in light curves, infrared emissions, and other data points that might indicate the presence of a Dyson sphere. For example, AI can quickly identify unusual dimming patterns in stars, like those seen in Tabby's star, and flag them for further investigation. This ability to process and analyze data at incredible speeds allows scientists to focus their efforts on the most promising targets. One of the most exciting applications of artificial intelligence in this field is its ability to detect anomalies that might otherwise go unnoticed. By comparing new observations with vast datasets of known stellar behavior, AI can spot deviations that could hint at artificial megastructures. This approach has already led to the discovery of several intriguing candidates, including stars with irregular light fluctuations that defy conventional explanations. Moreover, artificial intelligence is helping to refine the search by reducing false positives. Natural phenomena, such as dust clouds or planetary transits, can sometimes mimic the signatures of Dyson spheres. AI algorithms are being trained to distinguish between these natural occurrences and potential artificial structures, improving the accuracy of the search and saving valuable time for researchers. The integration of artificial intelligence into the search for Dyson spheres also highlights the collaborative nature of modern science. Projects like Planet Hunters and the SETI Institute are leveraging AI to engage both professional astronomers and citizen scientists in the hunt for extraterrestrial intelligence. This fusion of human curiosity and machine precision is accelerating discoveries and bringing us closer to answering one of humanity's most profound questions. As we look to the future, the role of artificial intelligence in this search will only grow. With advancements in AI technology and the launch of next-generation telescopes, the potential for groundbreaking discoveries is immense. Each new candidate identified brings us one step closer to understanding whether Dyson spheres are a reality and whether we share the universe with other intelligent civilizations. Now, let's venture into one of the most intriguing and speculative areas of this cosmic mystery: the potential connection between dark matter and Dyson spheres. Dark matter, that invisible and enigmatic substance that makes up a significant portion of the universe, has long puzzled scientists. Its gravitational effects are undeniable, yet it remains undetectable through conventional means. Could this elusive material hold the key to understanding why Dyson spheres have been so difficult to find? Some theorists propose that dark matter might play a role in the construction or operation of Dyson spheres. Imagine an advanced civilization harnessing dark matter as a resource, using its unique properties to build or power these megastructures. If dark matter interacts with ordinary matter in ways we don't yet understand, it could provide a means of energy collection or structural stability that goes beyond our current technological imagination. This idea opens up a fascinating possibility. Dyson spheres might not just be made of visible materials but could incorporate dark matter in ways that make them nearly invisible to our telescopes. Another speculative theory suggests that dark matter could be the reason we haven't detected Dyson spheres yet. If these megastructures are designed to interact with or even absorb dark matter, their signatures might be hidden within the very fabric of the universe. This would explain why our searches for infrared emissions or unusual light patterns have come up short. Instead of looking for traditional signs of energy collection, scientists might need to explore entirely new methods of detection that account for the influence of dark matter. Of course, these ideas remain highly speculative as our understanding of dark matter is still in its infancy. However, the intersection of dark matter and Dyson spheres offers a tantalizing avenue for future research. By exploring these theories, we not only push the boundaries of our knowledge but also challenge ourselves to think beyond the limits of current technology and physics. Could dark matter be the missing piece in the puzzle of Dyson spheres? Only time and further exploration will tell. As we continue to unravel the mysteries of the cosmos, the connection between dark matter and Dyson spheres reminds us that the universe is far stranger and more complex than we can imagine. And with every new discovery, we inch closer to understanding whether these megastructures are out there waiting to be found. Now, let's shift our gaze from the mysteries of the cosmos to a future closer to home, a future where humanity itself might embark on the monumental task of building a Dyson sphere. Imagine, for a moment, a civilization so advanced that it has mastered the ability to harness the energy of its own star. What would it take for humanity to reach such a level of technological prowess, and what would the implications be for our planet and species? The first challenge lies in the sheer scale of such a project. Constructing a Dyson sphere would require resources on an unprecedented level. We're talking about dismantling entire planets, asteroids, and moons to gather the raw materials needed. This alone would demand advancements in space mining, robotics, and engineering that far surpass our current capabilities. But beyond the physical resources, there's the question of energy. How would we power the construction process itself? Perhaps we'd need to develop new forms of energy generation, such as fusion reactors, to sustain the effort over centuries or even millennia. Then there's the matter of design. A Dyson sphere isn't just a single, solid structure. It's more likely to be a swarm of smaller satellites or panels orbiting the Sun, collectively capturing its energy. This would require breakthroughs in materials science to create lightweight, durable components that can withstand the harsh conditions of space. We'd also need to solve the problem of maintaining and repairing these structures over time, which could involve fleets of autonomous robots or even self-repairing materials. But let's not forget the societal and economic implications. Building a Dyson sphere would be a global endeavor, requiring cooperation on a scale humanity has never achieved before. It would demand a unified vision, shared resources, and a commitment to long-term goals that transcend national borders. This raises questions about governance, equity, and the distribution of benefits. Who would control the energy harvested from the Sun, and how would it be shared among the people of Earth? The impact on Earth's future would be profound. A Dyson sphere could provide virtually limitless energy, eliminating our dependence on fossil fuels and addressing climate change. It could power advanced technologies from interstellar travel to artificial intelligence, transforming every aspect of our lives. But it could also reshape our relationship with the planet. With the ability to harness the Sun's energy, we might no longer need to exploit Earth's resources, allowing ecosystems to recover and thrive. Of course, this vision is still far beyond our reach, but by imagining such a future, we challenge ourselves to think bigger, to push the boundaries of what's possible, and to consider the kind of civilization we want to become. The journey toward building a Dyson sphere isn't just about technological achievement, it's about the choices we make as a species and the legacy we leave for generations to come. And as we continue to explore the mysteries of the universe, we might just find that the greatest discoveries are the ones we make about ourselves. Now, let's take a step back and consider the deeper questions that the search for Dyson spheres brings to light. Beyond the technical challenges and scientific intrigue, this pursuit forces us to confront profound philosophical questions about our place in the universe and the nature of intelligence itself. What does it mean for humanity to search for signs of civilizations capable of harnessing the energy of an entire star? And what does it say about us if we never find them? At its core, the search for Dyson spheres is a search for meaning. It's a quest to understand whether we are alone in the cosmos or part of a larger tapestry of intelligent life. The very idea of a Dyson sphere challenges us to think about the trajectory of civilizations, how they evolve, what they value, and how they interact with their environment. Are we destined to follow a similar path, or is there another way forward? These questions push us to reflect on our own priorities as a species. Are we focused solely on survival and growth, or do we have a greater purpose in the grand scheme of the universe? The nature of intelligence itself is another central theme. If we were to discover a Dyson sphere, it would imply the existence of a civilization far more advanced than our own. But what does advanced truly mean? Is it simply a matter of technological prowess, or does it encompass ethical, cultural, and philosophical maturity as well? The search for Dyson spheres invites us to consider what it means to be intelligent, not just in terms of problem-solving and innovation, but in our ability to coexist with the universe and each other. Moreover, the possibility of finding a Dyson sphere raises questions about the limits of human understanding. Are we capable of comprehending the motivations and intentions of a civilization that operates on such a vast scale? Or would their existence remain forever beyond our grasp, a mystery that defies explanation? This uncertainty humbles us, reminding us that for all our achievements, we are still in the early stages of our cosmic journey. Finally, the search for Dyson spheres challenges us to think about our legacy. If we were to build one ourselves, what would it say about our values and priorities? Would it be a testament to our ingenuity and ambition, or a warning about the dangers of unchecked expansion? These questions force us to confront the ethical dimensions of our actions, not just for ourselves but for future generations and the universe as a whole. In the end, the search for Dyson spheres is as much about exploring the outer reaches of space as it is about exploring the inner reaches of our own minds. It's a journey that compels us to ask who we are, what we value, and what kind of future we want to create. And perhaps in seeking answers to these questions, we'll find that the greatest discoveries are not out there among the stars, but within ourselves. Shifting our focus to the broader picture, the search for Dyson spheres isn't just a scientific endeavor, it's a global one. International collaboration plays a crucial role in advancing our understanding of these cosmic mysteries. Space research, by its very nature, requires resources, expertise, and technology that no single nation can provide alone. By pooling knowledge and capabilities, countries around the world can tackle challenges that would otherwise be insurmountable. Take, for example, the collaborative efforts behind projects like the James Webb Space Telescope. This groundbreaking observatory, a product of cooperation between NASA, the European Space Agency, and the Canadian Space Agency, has already revolutionized our ability to study distant stars and their potential megastructures. Without such partnerships, the tools needed to detect and analyze Dyson Sphere Candidates simply wouldn't exist. It's through these shared missions that we've been able to gather the data necessary to explore these enigmatic phenomena. But international collaboration goes beyond just sharing technology. It also fosters a diversity of perspectives. Scientists from different cultural and academic backgrounds bring unique insights to the table, enriching the search for Dyson spheres. This diversity of thought is essential when dealing with questions as complex and multifaceted as the existence of advanced extraterrestrial civilizations. By working together, researchers can challenge assumptions, refine theories, and uncover new possibilities that might otherwise go unnoticed. Moreover, global cooperation helps ensure that the search for Dyson spheres remains a priority. Space exploration is expensive and resource-intensive, and political or economic challenges can often sideline ambitious projects. However, when nations unite around a common goal, they can secure the funding and support needed to keep these investigations moving forward. This collective commitment not only accelerates progress but also sends a powerful message about humanity's shared curiosity and determination to explore the unknown. The search for Dyson spheres also highlights the importance of open data sharing. Many of the most intriguing candidates, like Tabby's star and EPIC 204278916, were discovered thanks to publicly available datasets from missions like Kepler and TESS. By making this data accessible to researchers worldwide, we've enabled a global community of scientists, amateur astronomers, and citizen scientists to contribute to the search. This democratization of knowledge ensures that no potential discovery slips through the cracks. In a world often divided by borders and ideologies, the search for Dyson spheres reminds us of what we can achieve when we work together. It's a testament to the power of collaboration, showing that the pursuit of knowledge transcends national interests and unites us in a shared quest to understand the cosmos. As we continue to explore the mysteries of the universe, it's this spirit of cooperation that will light the way forward. Looking ahead, the next frontier in our exploration brings us to the most promising Dyson Sphere candidates of today's stars that continue to captivate scientists and enthusiasts alike. What makes these candidates stand out, and what secrets might they hold? Let's dive in. Now, let's turn our attention to the stars that have captured the imagination of scientists and space enthusiasts around the world, the most promising Dyson Sphere candidates of today. These celestial objects, with their unusual behaviors and tantalizing mysteries, stand at the forefront of our search for advanced extraterrestrial civilizations. What makes them so intriguing, and why do they continue to spark such fascination? First on the list is KIC 8462852, better known as Tabby's star. This star, located approximately 1,400 light-years away, first made headlines with its erratic dimming patterns. Unlike typical stars which dim in predictable cycles, Tabby's star exhibits sudden and dramatic drops in brightness, sometimes by as much as 22%. While natural explanations such as dust clouds or cometary debris have been proposed, the possibility of an artificial megastructure like a Dyson sphere remains a compelling theory. Its unpredictable behavior keeps scientists on their toes, making it one of the most studied and debated objects in the search for extraterrestrial intelligence. Next, we have EPIC 204278916, a young star located in the upper Scorpius region. This star has shown even more extreme dimming events, with its brightness dropping by up to 65%. Such drastic fluctuations are difficult to explain through natural causes alone, leading some researchers to speculate about the presence of a partially constructed Dyson sphere or a swarm of orbiting structures. While stellar activity and planetary debris are also considered, the sheer scale of its dimming continues to make it a prime candidate for further investigation. Another intriguing object is TYC 6111-1162-1, a star that exhibits a unique light curve unlike anything seen before. Its irregular dimming patterns, combined with its distance and the challenges of studying it, have made it a subject of intense interest. While natural explanations such as a circumstellar disk or a swarm of asteroids have been proposed, the possibility of an artificial megastructure cannot be ruled out. Its enigmatic behavior ensures it remains a key focus in the search for Dyson spheres. What ties these candidates together is not just their unusual light patterns, but also the questions they raise about the nature of advanced civilizations. Could these stars be surrounded by megastructures designed to harness their energy? Or are we witnessing entirely new astrophysical phenomena that challenge our understanding of the universe? The answers remain elusive, but the pursuit of these mysteries continues to drive scientific inquiry and public fascination. As we look to the future, advancements in technology and international collaboration promise to shed new light on these enigmatic stars. Missions like the James Webb Space Telescope and upcoming observatories will provide unprecedented insights, bringing us closer to understanding whether these candidates are the work of nature or something far more extraordinary. The search for Dyson spheres is far from over, and these stars remind us that the universe is full of surprises waiting to be uncovered. Looking ahead, the search for Dyson Sphere Candidates is poised to enter an exciting new era, driven by cutting-edge technology and innovative approaches. As we continue to refine our methods and expand our observational capabilities, the potential for groundbreaking discoveries grows exponentially. Imagine the possibilities. What if the next star we observe reveals unmistakable signs of an artificial megastructure? Such a discovery would not only confirm the existence of an advanced extraterrestrial civilization, but also fundamentally alter our understanding of the universe and our place within it. One of the most promising tools in this quest is the James Webb Space Telescope, which has already begun to revolutionize our ability to study distant stars and their surrounding environments. With its unparalleled sensitivity to infrared light, the telescope could detect the faint heat signatures that a Dyson sphere or similar structure would emit. This capability opens up a new frontier in the search for extraterrestrial intelligence, allowing us to probe deeper into the cosmos than ever before. Future missions, such as the planned Nancy Grace Roman Space Telescope, will further enhance our ability to identify and analyze these enigmatic objects, bringing us closer to answering one of humanity's most profound questions: are we alone? Beyond telescopes, advancements in artificial intelligence and machine learning are transforming how we process and interpret astronomical data. These technologies enable us to sift through vast amounts of information with unprecedented speed and accuracy, identifying patterns and anomalies that might otherwise go unnoticed. As these tools become more sophisticated, they could uncover new Dyson Sphere Candidates or even detect subtle signs of extraterrestrial engineering that challenge our current understanding of physics and technology. The implications of such discoveries extend far beyond the realm of science. Finding evidence of a Dyson sphere would not only validate decades of theoretical speculation, but also inspire a new era of exploration and innovation. It would force us to reconsider our assumptions about the limits of technology and the potential for civilizations to harness the energy of their stars. Moreover, it would spark a global conversation about the ethics and consequences of contacting an advanced extraterrestrial species, raising questions about how we might communicate, collaborate, or coexist with such a civilization. As we stand on the brink of these potential breakthroughs, it's worth reflecting on the profound impact they could have on our collective imagination and aspirations. The discovery of a Dyson sphere would be a testament to the ingenuity and curiosity that drive humanity to explore the unknown. It would remind us that the universe is vast, mysterious, and full of possibilities, and that the search for answers is as much about the journey as it is about the destination. With each new discovery, we take another step toward unraveling the secrets of the cosmos, and perhaps toward finding our place among the stars. Now, let's turn our attention to the role of public engagement in the search for Dyson spheres and other cosmic mysteries. The fascination with space exploration isn't confined to scientists and researchers. It's a shared passion that captivates people from all walks of life. This widespread interest plays a crucial role in driving funding and support for scientific endeavors. making it possible to pursue ambitious projects that might otherwise remain out of reach. Public engagement often begins with storytelling, when scientists and educators share the wonders of the universe in ways that resonate with everyday experiences. They spark curiosity and inspire a sense of connection to the cosmos. Think about the excitement generated by discoveries like Tabby's star or the potential of the James Webb Space Telescope. These stories don't just stay within academic circles. They spread through social media, documentaries, and even casual conversations, drawing more people into the conversation about space and its mysteries. This growing interest translates into tangible support. Crowdfunding platforms, for example, have enabled citizen scientists to contribute directly to research projects, from analyzing star data to building small-scale telescopes. Programs like Planet Hunters, which invite the public to sift through astronomical data, have not only advanced scientific research but also fostered a sense of ownership and participation among enthusiasts. When people feel involved, they're more likely to advocate for increased funding and resources for space exploration. Moreover, public engagement helps bridge the gap between science and society. By making complex ideas accessible and relatable, scientists can build trust and enthusiasm for their work. This, in turn, encourages policymakers to prioritize funding for space research, recognizing its value not just as a scientific pursuit, but as a source of inspiration and innovation for humanity as a whole. The impact of public engagement goes even further. It shapes the next generation of scientists, engineers, and dreamers. When young people see the excitement surrounding discoveries like Dyson Sphere Candidates, they're inspired to pursue careers in science, technology, engineering, and mathematics. This creates a ripple effect, ensuring that the quest to understand the universe continues for generations to come. In essence, the search for Dyson Spheres isn't just a scientific endeavor. It's a collective journey that unites us in curiosity and wonder. By engaging the public, we not only advance our understanding of the cosmos, but also strengthen the bonds that connect us as a species, reminding us that the stars above are a shared inheritance waiting to be explored. As we reflect on the enduring fascination with Dyson spheres and the mysteries of the cosmos, it's impossible not to acknowledge the visionary mind behind the concept, Freeman Dyson. A physicist, mathematician, and dreamer, Dyson's contributions to science extend far beyond the theoretical megastructure that bears his name. His work has left an indelible mark on our understanding of the universe and our place within it. Dyson's brilliance lay not just in his ability to solve complex problems, but in his capacity to imagine possibilities that others might dismiss as science fiction. When he proposed the idea of a Dyson sphere in the 1960s, he wasn't merely suggesting a way to harness stellar energy. He was challenging us to think bigger, to consider what an advanced civilization might achieve. This bold vision has since become a cornerstone in the search for extraterrestrial intelligence, inspiring generations of scientists and enthusiasts to look for signs of such megastructures in the stars. But Dyson's legacy goes even deeper. He was a champion of interdisciplinary thinking, blending physics, biology, and philosophy to explore questions that transcended traditional boundaries. His ideas on topics like the origins of life, the future of technology, and the ethics of space exploration continue to spark debate and innovation. Dyson understood that science isn't just about answering questions, it's about asking the right ones, even if they seem impossible to answer at first. Perhaps one of his most enduring contributions is the way he bridged the gap between science and imagination. Dyson's work reminds us that the pursuit of knowledge is as much about creativity as it is about calculation. His willingness to dream big has inspired countless researchers to push the limits of what we think is possible, whether they're searching for Dyson spheres, designing new telescopes, or pondering the nature of intelligence itself. Today, as we continue to explore the cosmos and unravel its mysteries, Freeman Dyson's ideas remain a guiding light. They remind us that the universe is full of wonders waiting to be discovered, and that the search for answers is a journey worth taking, no matter how far it leads us. His legacy is not just in the theories he proposed, but in the curiosity and courage he instilled in all of us to look up at the stars and wonder what might be out there. With this in mind, let's turn to the final thoughts of our exploration, where we'll tie together the threads of these 25 space mysteries and reflect on what they mean for the future of humanity's quest to understand the cosmos. As we bring our journey through these 25 space mysteries to a close, one thing is clear. The allure of Dyson spheres and the enigmatic phenomena surrounding them continues to captivate our imaginations. From the peculiar dimming of Tabby's star to the erratic light patterns of epoch 204278916, each mystery invites us to question what lies beyond our current understanding. These cosmic puzzles remind us that the universe is vast, complex, and full of secrets waiting to be uncovered. The search for Dyson spheres is more than just a scientific endeavor. It's a testament to humanity's unyielding curiosity and our desire to connect with something greater than ourselves. Whether these megastructures are the work of advanced civilizations or the result of natural phenomena we've yet to fully comprehend, they challenge us to think beyond the limits of our knowledge and explore the possibilities of what might exist among the stars. But the story doesn't end here. Every discovery, every observation, and every unanswered question brings us one step closer to unraveling the mysteries of the cosmos. The tools and technologies we have today, from the James Webb Space Telescope to the power of artificial intelligence, are opening new doors in our quest for understanding. And as we look to the future, the potential for groundbreaking discoveries grows ever brighter. So, what can you do to be part of this incredible journey? Stay curious, follow the latest developments in space exploration, engage with the scientific community, and support initiatives that push the boundaries of what we know. Whether you're a seasoned space enthusiast or someone just beginning to explore the wonders of the universe, your curiosity and passion matter. Together, we can continue to unlock the secrets of the cosmos and inspire future generations to look up at the stars with wonder. If you've enjoyed this exploration of space mysteries, don't forget to like this video, subscribe to the channel, and hit the notification bell so you never miss an update. Let's keep the conversation going. Share your thoughts in the comments below. What do you think about the possibility of Dyson spheres? Which of these 25 mysteries fascinates you the most? The universe is waiting and the adventure is just beginning. Thank you for joining me on this journey, and remember, the stars are not the limit, they're just the